You can see the screen. What can you all see? Neutralization. Okay, yeah, I see. Okay, right. So yesterday, just to go through quickly what we did from acids and bases from the beginning, just a 1 minute replay. We did acids and bases. We first looked at what is an acid and what is a base. There's an Arrhenius definition and there's a Laurie-Bronsted definition, right? So we did that. And our focus is an acid is a proton donor and a base is a proton acceptor. Then we went into the common acids and bases that you get. And the common acids and bases that you get HCl, H2SO4, HNO3, and CH3COOH, acetic acid or vinegar, ethanoic acid. Common bases, NaOH, sodium hydroxide, sodium hydrogen carbonate, sodium carbonate, ammonia. Then we went into ionization reactions. We said acids ionize, and sometimes you get dissociation, like in the sodium hydroxide, the base that we did. And then we had, for example, HCl. When you put it in water, you get H3O+, which is your hydronium ion or oxonium ion, and Cl-. And then we did another example, NH3 plus H2O gives you NH4 plus OH-. And then we looked at dissociation. If you take a base like sodium hydroxide and if you put it in water, we see that the water breaks up the sodium hydroxide crystal into Na plus and OH minus ions. Then we said, let's look at conjugate acid-base pairs. And then we looked at an example, HCl, H2 plus H2 gives you H3O plus Cl minus. And we said we must look at the common ones that are common. If you look at HCl, it looks similar to Cl minus. And if you look at H2O, it looks similar to H3O plus. And then we said that in order for us to determine which is the acid and the base, we'll see which one's got an extra H plus. So if you look at HCl and Cl minus, which one's got an extra H plus, it will be the HCl. So HCl is your acid. So HCl is your acid one, and Cl minus will be your base one. All right. Then we went further to say that, let's look at another example. Let's just make the slideshow bigger. We looked at NH3 and H2O will give you NH4 plus and OH minus ions. And then we see that we looked again, NH3 and NH4 plus look similar. The one with the extra H plus is your acid. So therefore NH4 plus is your acid and NH3 is your base. And then similarly with H2O and OH minus, the same thing applies where H2O has an extra H plus compared to OH minus. So H2O is your acid and OH minus is your base. Then you'll have homework. Then we looked at ampholites, and we said an ampholite is a substance that can act as an acid or a base. You look at HCl plus H2O gives you H3O plus Cl minus. So in this case, we look at HCl, we look at H2O and H3O plus. The H3O plus is your acid, so your H2O is your base in the first case. Then if you take NH3 plus H2O gives you NH4 plus OH minus, then we see that if you compare H2O and OH minus, then H2O will be your acid. So H2O can act as an acid or a base depending on what it is reacting with. Then we looked at another example, HSO4 minus. And I said, let's look at HSO4 minus. And we said, if you take H2SO4 plus H2 gives you HSO4 minus plus H2O. So in this case, we see that H2SO4 is your acid and HSO4 minus is your base. Mark for that. Then if you look at another example, HSO4 minus plus H2O gives you SO4 2 minus plus H2O. Then if you look at HSO4 minus and SO4 2 minus, we see SO4 2 minus is your conjugate acid and HSO4 minus will be your conjugate base. So in the one reaction, HSO4 minus acts as an acid and in this case, and in the other case, HSO4 minus can act as a base. And then if we do the full reaction, we see that H2SO4 plus 2H2O gives you SO4 2 minus plus 2H2O. So your HSO4 acts as your acid and here HSO4 minus X is your base. All right, so if you go further, we said a strong acid and a weak acid. A strong acid ionizes completely in water, or more than 90%. For example, if you take HNO3 plus H2O, it becomes H3O plus NO3 minus. And if you look at the arrows, because it's a reversible reaction, we can say that H3O plus, most of the HNO3 ionizes to form H3O plus ions. So the reaction, the balanced reaction lies far to the equilibrium of the reaction lies far to the right. Then if you look at a weak acid, for example, acetic acid or ethanoic acid plus water gives you H3O plus CH3 COO minus. And here the reverse reaction is favored because it's a weak acid, so the equilibrium lies far to the left. Concentrated and dilute acid, we said a concentrated acid, basically we have to look at C is equals to N over V. A concentrated acid has a high number of moles in the volume of water, and a weak acid, a dilute acid is one that has a small number of moles in a given number of water, right? Then the question was, can we get a concentrated weak acid or dilute strong acid? Yes, we can. If you look at NH4CO3, it is constant. If it's yes, it's concentrated if you put a high number of moles in a small number of water. NaHCO3 is a base. It's a weak base, but it can be concentrated if the number of moles in the water are high. A dilute strong base, NaOH, low number of moles and high concentration of water, is a dilute strong base, because NaOH is a strong base, and if you put a low number of moles in lots of water, in high concentration of water, it will be a dilute strong base. Right, and we looked at the types of reactions: acid plus metal, salt plus hydrogen, acid plus metal oxide, salt plus water, acid plus metal hydroxide, salt plus water. We're going to concentrate on, not necessary. Acid plus carbonate, salt plus water plus carbon dioxide. The carbonate effervescence makes an effervescence, we mix water and we make carbon dioxide bubbles. Acid plus ammonia gives you ammonium salt. And the example was HCl plus NH3 gives you NH4Cl because it combines. Then we looked at examples of the preparation of the different salts, which I won't go into now. And then you had your homework to do, right? And then we just completed to say a monoprotic acid is a acid that donates one proton, for example, HCl, and a diprotic acid is an acid that has two protons available to donate, for example, H2SO4. All right. Then today we're looking at titration, neutralization reactions. The reaction between an acid and a base is known as a neutralization reaction. So when an acid reacts with a base, you get a neutralization. The acid and the base will neutralize each other. So the example that they said we must use for grade 12 at the moment will be H2C2O4, which is a weak acid. Oxalic acid, right? This is called oxalic acid. Write this down, please. Let's just put this, write it down nicely. This is oxalic acid. Oxalic acid. So if you take oxalic acid, which is H2C2O4 plus a strong base NaOH, which is, what's the name of NaOH? Let's just write it down since we're busy with it. Will be sodium hydroxide, right? And that's going to give you, if you balance it out, it's going to give you sodium oxalate plus water, right? So that's what we've got. Okay, so now if we react the acid with a base, we mix the sodium oxalate plus water. Now, how the question is, how do we do the reaction, right? So in order to do the reaction, we need a specific indicator also to show when we're going to reach endpoint. So when the acid reacts with the base, when is the reaction complete? When there's possible completion of the reaction? So in order to do that, we have to choose an indicator. An indicator is a substance that indicates the end point of neutralization by changing its color at the end point. So the color will change. For example, bromothymol blue is yellow in an acid and blue in a base. Methyl orange is red in an acid and orange or yellow in a base. Actually, we should rather say yellow here, right? Yellow in a base, right? Let's just go back a little bit. We should say yellow in a base. Phenolphthalein or phenolphthalein, colorless in an acid, pink in a base. And then what is it? How do you know when is the end point? So to know the end point, we just wrote this down here. I don't know if you can see everything. Bromothymol blue is yellow, in an acid blue in a base. Color at end point, it's green. Methyl orange is red and usually yellow, and it's darker between the darker orange in the at the end point. And phenolphthalein is colorless in an acid and pink in a base, and it's a lighter pink when it becomes neutral, when it reaches endpoint. Okay, there's something called endpoint and equivalence point. We don't have to concentrate too much on this. I just said I'll write it down. The term equivalence point means that the solutions have been mixed in exactly the right proportions according to the equation. For example, if you look at our equation, we've got 1 mole of oxalic acid and 2 moles of sodium hydroxide. So it must be added in the proportion 1:2. So that's what we're talking about, right? So when the ratio of is 1:2, whether it's full 1 mole to 2 moles or half a mole to 1 mole, whatever the case is, then we've reached equivalence point. However, the term endpoint is where the indicator changes color. As you will see on the page about indicators, this isn't necessarily exactly the same as the equivalence point. I just pasted it from somewhere, I think, so don't worry about this page business, right? We choose an indicator so that the equivalence point is as close to the end point as possible. So we try to maybe more or less make it similar. Now, what I think I'll do at this point in time is share another screen to show you the end point of a titration reaction. All right, let's just see. Oops. Method to prepare. Give me 1 second. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will be discussing titrations. And if you look at the question that we have in front of us, 7.96 grams of NaOH were dissolved in 250 cm cube of water. 25 centimeters cube of this solution was titrated against an unknown concentration of HCl. If 31.5 centimeters cube of HCl was used to reach endpoint, calculate the concentration of the HCl. Now, to do this titration, we will actually do this question in the lab, and from there we will see where do we get the 7.96 grams, how will we use the NaOH, where do we get the 25 centimeters cube of the NaOH solution, where do we get the 31.5 centimeters cube of HCl, and how we can use these values and where we can find these in the apparatus in the lab to find the concentration of the unknown HCl. So let us begin. One second. I've got sodium hydroxide there. Okay, hold on. I'm not showing you the right video. What you must do is you take your sodium hydroxide and we're going to crush it using a mortar and pestle. Okay, just to get back, am I showing you the color? What can you see on the screen? Are you seeing the phenolphthalein color change at endpoint? Talk to me. Somebody talk to me.
No, my screen is blank.
What can you see now?
Now I see the video.
Okay, I'm just playing this video, right? I did this video some time back. We basically titrating the oxalic acid versus the sodium hydroxide. Now we're looking for endpoint. Let's see if we get endpoint. Listen carefully. Right. Can you all see the whole screen now? Sorry, guys. Can you all see the whole screen? Can you all see the picture clearly? Hello. Talk to me. I don't know what I'm showing you. Okay, so we see.
We can.
So it's clear. Can you see it's clear? If you look at the picture now, it's colorless, right? So we put phenolphthalein there, and now we're adding the base to it, from the burette on the top. One drop makes a difference.
Now it's still white. So we take the volume here to be safe. The volume here is 17 centimeters cubed. 17. This is the volume of base that neutralize that acid. It's actually 16, 17,1. It hasn't yet. Now we're trying to be safe, huh? So now we take one more drop. There's a one drop. That's it. One drop. Now to be 100% sure, you must take the wash bottle and wash out any color is turned pink. So this is N. Right. So no, but it's not white. Come see. It's not white. So this is end point. Because now if I put more, the pink. It's a pale pink. Yeah, this is just start like light pink. But if I put one more drop, it will turn dark pink. So it's almost yes, correct. Now let's try one more drop. Sometimes one drop won't make a difference, but two or three, but not much more. Let's go. We're going one drop at a time. Can you see why it's important to hold it like this? Control and drop. One drop. There, you saw the difference. So we were definitely at endpoint. We were lucky. We got it nicely first off.
Okay, guys, are we back? I don't know if you all saw the video or not. Things look a bit. Did you all see the video? AK, you saw the video?
It is just lagging a bit.
Okay, but you all saw the video. Did you see endpoint? Did you see it was pink? It was light pink and then it became dark pink with one drop. Did you all see that? Hello? Can somebody answer me? Shoaib, you saw that?
G.
Okay, so we saw endpoint, right? Hopefully when we get back to class, we will do it again. So we got an idea of what is endpoint now, right? It's the point at which the indicator changes color. And what we try and do is we choose an indicator so that the equivalence point is as close to the endpoint as possible. So more or less when the reaction is complete. Now they haven't yet asked this in the exam, but nothing stops them from asking it, is that how do you draw a graph, a titration graph? So if you titrate a strong acid with a strong base, then your endpoint is around 7, or your equivalence point as well in this case. So the suitable indicator is an indicator that changes color around pH 7. That's why I put it here on the graph. So the best indicator to use will be bromothymol blue, because bromothymol blue will turn green at endpoint. Okay, so bromothymol blue is the best indicator. We see here that you got an acid and the pH of the acid is low, and as you're adding base to it, the pH goes higher and higher. And the more base you add, the pH goes higher and higher. And when it reaches that end point, that one drop will make it reach end point where the color turns green. I've got a video on that. I'll send it to you on the WhatsApp, right? So a strong acid and a strong base, bromothymol blue is the best indicator to use. If you got a strong acid and a weak base, then the strong acid, here's it, you're starting at a very low pH, and then the indicator, if you have a strong base, a strong acid and a weak base, the weak base is just above 7, maybe it's 9 or something. So the end point will be around 4. So the best indicator, most suitable indicator to use will be methyl orange. If you're using a weak acid with a strong base, then the weak acid and a strong base, the weak acid, the pH is closer to 7 and the strong base is closer to 14. And then when the two combine in a titration, the endpoint will be around 9 or so. There we've got 9. So a suitable indicator that we will use is phenolphthalein, as the video I showed you, right? This is an example just to say if you're titrating the acid to the base, then the diagram looks like this curve. But if you're titrating a base to the acid, then the curve starts at the top and it comes down. So this two is the same, but it's acid, when you're titrating acid to base, when you're putting the base into the acid, and the other one is the acid into the base, right? Depending on where you're taking the pH first. So now we come to titration calculations. To calculate titrations questions, use the following equation. I want you to write this down. CAVA all over CBVB is equals to NA over NB. So write that down. So you look at CA will be concentration of acid, VA will be volume of acid, concentration of base, CB, VB volume of base, number of moles of acid over number of moles of base. Now let's look at an example. During a titration, Aisha finds that exactly 15 centimeters cube of KOH. So what does that refer to? Write on your data. If you got KOH, KOH is an acid or a base? KOH will be your base, right? KOH is your base. So this is your base. And then 15 centimeters cube will be your volume of your base. All right, volume of base. Neutralizes 20 centimeters cube of H2SO4. So H2SO4 will be your acid. This will be your acid. And your volume of your acid will be 20 centimeters cube. Right, if the concentration of the KOH is 0.2 mole per dm cube, so you're given the concentration of your base. This is your base. Calculate the concentration of your acid. So how do we do that sum? So what we do is we write down our data. Write down our data. Let's just take all those things away. So write down your data. Right, so during a reaction, we find that 15 centimeters cube of KOH. So we got 15. Now, because you're working in centimeters cube and centimeters cube here, both of them are centimeters cube, the centimeters cube will cancel out, so you don't have to convert directly, right? So we see that what we can say is, let's write down what we've got. Let's look at it. So 15 centimeters cube of KOH. So here's your 15 centimeters cube. All right. And then your other things that you have, 15 centimeters cube is given. All right. And then 20 centimeters cube of H2SO4, 20 centimeters cube is given. Today is one of those days, yeah. CaVa, your volume of your acid, is this thing right or is it wrong? Let's see. Ca, we got the 15 centimeters cube of base, so 15 is base, right? So 15 must be your base. Let's go here. 15 centimeters cube of KOH. So your base, Vb, is it? Vb is 15 centimeters cube, right? It's there. And then 20 centimeters cube of acid, Va is 20 on the top. That's correct. And then your concentration of your base is 0.2 mole per dm cube. You put it here. And then your concentration of the acid is what you must find, right? So those four values are correct according to this equation. And Na over Nb, number of moles of acid over number of moles of base. Where do we get that? What's your number of moles of acid? We have to look at our balanced equation. One acid is 1 mole and NaOH is 2 moles. So one acid and is reacting with 2 base, right? So acid is 1 and base is 2. Then if you want to work out Ca, we take everything onto the other side. The 0.2 times 15, we cross multiply, we put it on the top, 0.2 times 15. And Ca times 20, you divide by C20 on both sides, so it becomes 2 multiplied by 20, and you got 0.075 moles per dm cube as the concentration of the acid. So write this down carefully.